and torsion. Okay, I think I'll just go through one of the types of questions then. I'll probably have enough time for 3. Do you guys have a preference of? I'll probably start with inertia just because it's like where we start, and I'll do a question with Moore circle. Are you guys comfortable with Moore circle? Because Moore circle is quite confusing, especially when you mix it up with shear and strain. Okay. If you want a copy of my notes, I have the QR code here.
Ask for a code.
Ask for a code? Okay, I'll...
Send you Gmail. It's gonna get like hundreds of emails.
Oh dear. Oh yes, I'm getting a lot. Okay. Okay, stop. Let me try and see if I can. Okay, give it a go. Maybe it'll work. Is it working now?
No.
No?
Send you another email.
Interesting. Okay. I'll try to fix it up after, and then I can get you guys. You guys can probably just go through the questions with me then. That'll probably be the best way to do it. Just 1 second. Okay. Okay, so this is the first question we're going to be looking at. I would say most of the questions regarding transform section, so this is a transform section question. It will most of the time almost look like this. It will always be structured like this, and the steps will always be the same. So essentially, are you guys confident with transforming sections? Okay, so I'll just run through it first. So basically, the steps to do this are pretty much right in front of you. This is like pretty much going to be step 1, step 2, step 3, step 4, and step 5. And let's do the bending first. Bending is just ENGG2400. So it's not something that should really be the struggle. The struggle should be more in the end part with the stress transformation. So let's just do the bending first. Right off the bat, can anyone tell me like if they just know what the bending is for this cantilever? Just ignoring all of the left side. Yeah, so if you got 10, that's about right. Cantilever should look something like this. And you have reaction forces here. And also a moment about here. So then, just doing ENGG2400, you have your forces in the y direction. You get -5 times 2 plus ay. And then you get ay is equal to 10. And then for moment, pretty much the moment's a little bit different. Because for these questions, you're always trying to solve for the maximum bending moment. Because the maximum bending moment is wherever the beam is going to fail first. So essentially what that means is when a beam is bending so much, the section can only handle up to that much, pretty much. So when we're solving for this section in terms of the stresses that are being applied, we have to do it for the maximum moment. The maximum moment is just where it's the most extreme case, and when we're finding the most extreme stresses that is happening, it will always happen at the most extreme case. So for cantilevers, for example, it will happen at the end, because that's just the way they bend, like this. For beams, it will, a bending moment diagram for a beam looks kind of like this, right? So this is where your M star will be for a cantilever, and your M star for beams will typically be in the middle of your beam. If you have a situation where it's a little bit more nuanced and like you have a little bit of a weird reaction placement, then you will have to solve the shear force diagram or the bending moment equation for the beam, and then you'll have to find the bending moment from there. Like for example, the bending moment for this will look something like this, like that, and your M star will be here, if that makes sense. So this is like M max, M max, M max. And for this question, we have it at a cantilever. So it's safe to assume that it's going to be at the very end. And also, the way to do this is when you draw your shear force diagram, it'll kind of something like this, where this is 10, this is a plus. And your bending moment up until that point that you're looking at is going to be the area of the shear force diagram. So this is 2 meters. The area of this triangle is 10 times 2 times half. And you get 20 kilonewtons per meter at 2 meters. So this is at 2 meters. That's just the accumulation of all of the shear force into bending moment.
Is it 10 kilometers?
Oh yeah, 10. So MA is equal to 10, I believe. Yeah. All right. So now we'll get on to the actual 2400 part. So when you're looking at your section, you can either change it. You can change it to whatever you want. It doesn't really matter. Whatever you want is whatever you think is the easiest. You can change it from timber to steel or steel to timber. So if you change it from timber to steel, you'll get something that looks kind of like an I-beam, like this. And if you change it from steel to timber, you get something that looks kind of stubby like this. I'll just copy and paste this over so you guys can see. Okay, so do you guys see how the transformation kind of works? Just for a reminder, when you're transforming your section, it's only the breadth that changes. So basically what I'm saying is, if you guys remember your n factor, are you guys familiar with n factor? Yeah. So n is a before, the Young's elastic modulus of the material before to the material after. And in this case, it's going to be, we're doing timber to steel, so it's going to be 10 over 200. And you don't actually need to care about the unit conversion here because it's just a ratio. You just have to make sure that both of your elastic moduluses are in the same units. So yeah, it doesn't matter if it's in MPa or GPa, you can use it the same either way because it's just a ratio. So this will end up being 1 over 20. And for recap, this makes it so your breadth of the section changes by 1/20. It's not that all of the elements do. So if we're doing timber to steel, this section is the timber part, this section here. And instead of the timber elongating by, instead of the timber elongating by 1/20 and like the steel staying the same, and this breadth here, that breadth, elongating by 1/20, that doesn't happen. So what I'm saying is these heights and these depths maintain the same height, but the breadth changes. So this will still stay as 100 millimeters, sorry. And this width will change to 50 times 1/20. So that's just B times N, and you only do that for your transform sections. So in the end, you should get something that looks like this. Um, 2.5. Yep, and this is 50 millimeters. Yep. Does everybody get that? Yep. Okay, so now we find the y-centroid. This is just like partially inertia, which is why I kind of chose this question. Y-centroid, if you remember, is AI over yi over AI, sum of AI. It's just the sum of the area and, okay, sorry, wait. This is block 1, this is block 2, this is block 3. And I is basically the shape number. So if you sum it up, this will be 50 times 20 times, let's take the axes to here. That's the axes. And you'll get 110 and 20 plus 100 times 2.5 times 50, 60, plus 10 times 50 times 5, all over 50 times 20 plus 100 times 2.5 plus 10 times 50, and you should get something that looks like this, 78.57. So that's just finding y-centroid. Should be pretty simple. For inertia questions in particular, you guys might have noticed, but it is a lot of like just tedious menial work. You are going to just have to crunch through it if you get one that requires a lot of shapes, and there's no other way around it. So you just have to crunch through the numbers. So we're going to do that with IXX now. So do you guys, yeah, okay, we'll just go through it. Okay. So IXX is equal to like the sum of IXXI plus AI dyi squared. That's the parallel axis theorem. We can also say that x hat is equal to 0. Okay. And now you should get for shape 1, shape 2, shape 3. You should get 50 times 20 cubed. So it's, BD cubed on 12. That's BD cubed on 12. Okay, BD cubed on 12. This one will be 2.5 times 100 cubed on 12. This one will be 50 times 10 cubed on 12. And then let's do our parallel axis theorem. So that will be That'll be 120. 120 minus y hat squared. That'll be 60 minus y hat squared. And that'll be 5 minus y hat squared. So then after you sum all these numbers, your IXX should be, oh yes, times our area. All right, and then you should end up with 4784761.405. It's around the ballpark of 4.7 times 10 to the 6. Yeah. And that's like pretty much all of your inertia done. So that's like all the first part of solids, essentially. Now, here's a little bit of the more new stuff, which comes with stress. Basically, when you're looking at a stress distribution, you're thinking about like how it's what stresses are happening like to this beam at the very end. So you can kind of expect as well, if you guys remember, like in a way that a beam bends, in this situation it'll bend kind of like this. And then your tension fibers. Do you guys remember where the tension fibers and the compression fibers are? Yeah, so compression is at the top, and then tension's at the bottom. So for a cantilever, where it bends like this, you can expect it to be the opposite way. Okay, so now you kind of generally know that you can expect the stresses at the top to be positive, and the stresses at the bottom to be negative. Okay, that's like just a sanity check for at the end. So let's assess these points in particular. Here, 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 and the original question was to find the max of the stresses out of the whole section. So let's call this A, B, C, and D. And we're going to use this formula if you guys are familiar with it. Yeah, okay. And you can say the stresses at A is going to be M over, this is, I'll just go through this. This is going to be your moment in Newton millimeters. This is going to be your distance to neutral axis. And that's going to be your moment of inertia. Okay, so our M in this case, our M for all of our cases is going to be 10 times 10 to the power of 6. Yeah, 10 times 10 to the power of 6 Newton millimeters. And your Y can just be taken like from the position, so it'll be Y minus Y bar. And it will be 150, I believe. 130. Oh, wait. Oh, okay, my answer's wrong. 130 minus y bar over Ix. And you'll do this for every single point. So that's B is located 20 below the top, so it'll be 110. This one will be, which one? Oh. Yeah, that one will be 10. All right. And D. And you should get some numbers. I actually don't have the actual numbers. But this one goes to negative 107.48. Like that. MPA. This one goes to. Okay, I know the bottom two numbers.
For stress at A.
Yeah.
Is it from A to the central?
Yeah. So it's the distance here.
Oh, okay.
So the distance is just the distance from the point to the neutral axis. Yeah. And the neutral axis is y bar.
Half distance or from A?
So from A, it's the full distance.
Oh, full distance.
Yeah. Yeah. Wait.
Wait, if it's full distance, how D is zero?
Sorry?
If it's full distance, how D is zero? It's like diffuse from DNA.
What do you mean?
Well, because I thought you're doing from the NA, so point D would be like definitely not zero.
I think it's.
Minus.
Wait. I think I'm confusing myself. What the heck?
Oh, yeah.
Why?
So like it would be like minus something, minus 5 central.
I think it's. Oh, what the hell?
Because it's distant to
At the,
but if you draw the NA from the bottom, it would be
no. So it's like it's meant to be the distance to the neutral axis. So this point is at 0, and this is at 78, and then the distance is negative 78.
Yeah.
Yeah, I don't have the number for stress at A, but essentially, does anyone have the number for stress at A? No.
How you do it normally? The
174. Wait, what? Oh, okay. Oh, yeah. Wait, does anyone have the stress at B then? Just replace it with 110.
Negative 65.69. Yeah, that's fine.
Okay. So, basically, then, would you guys say that like we're kind of finished with this question? So, we're trying to find the maximum stress, right? The maximum stress you can actually get from all this. You can just say that the maximum is at 164.2 MPa, and that's going to be in compression. But when you're drawing, so another part of this question is to draw the stress distribution throughout the composite beam. So I'm just going to draw it. Essentially.
Sorry, Karen, real quick.
Yep.
Is there a rule for the signs of the stresses in the top section and the bottom section? Will the top section stresses always be positive to the
No. I think it's supposed to be. I think this is supposed to just like come up as negative, negative, positive, positive, but you should know like just based off this that it's going to be the opposite way.
Yeah, okay.
Yeah. Essentially, when you're drawing a stress distribution basically is like the triangle stuff that you guys probably have looked at, but you might not know what particularly means. So basically, this is a stress distribution. Do you guys kind of get the idea of what a stress distribution is? So it just means that throughout your cross-section, this might be experiencing a type of tension, and this way might be experiencing a type of compression. And then throughout, like as you go further down your section, it just experiences a different type of stress. So this is like a numerical value, and then as you go down the line, like each of those points are numerical values at different y values. That's essentially what stress is. In this case, could you say that our stress distribution looks like this? Okay. Would you guys say that we're done with this question now? This is all of part E. Yeah.
Sorry, why did you change the size?
Because based off this diagram, right, you kind of know that the top part of the section is going to be in tension, and you know the bottom part is going to be in compression. Yeah.
Minus like 130.
Yeah, I think you can. I'm actually not completely sure. I think just for convention, you should just write it the same way. And especially in a beam, you'll get it the same way as well. But just know off this. This is like your holy grail, pretty much. If you get a cantilever, it will be the opposite way. If you get a beam, it will be the normal way. So tension will be on the top for a cantilever, tension will be on the bottom for a beam. Yeah. And like positive is tension, negative is compression. You guys agree? Yeah. So let's go with this. Would you say that this question is done?
Yeah.
Okay, so this is actually an incorrect stress distribution. So if you remember, this part was transformed from timber to steel. So we need to actually convert it back to steel to timber. And the easiest way of doing that is by just multiplying the stresses at which your point is interested. So that's going to be like right before B, you have steel, and right after B, you have timber. So essentially, you're multiplying B and C because they're both the points we're interested in where the materials kind of change, and you're going to multiply them by 1/20. So in this, tension is positive.
You just flip your slides again?
Yeah, I just flipped it. Okay.
Would you be dividing by 1/20?
No, you're just timesing by 1.20.
I'll figure it out.
Maybe you are dividing it. And to get some really low number, probably like, just going to guesstimate this because I don't have a calculator on me. Like 3. Okay. Okay, so now what your stress distribution should actually look like. Should look like 107 MPa here. 65.69 MPa here. Then it goes down to 65.69 times 1/20. This is 7.1655. And then it goes back up to 143.3 and 164. 121. And then that will be your final stress distribution. And then that's when you can call this question finished. So if you have a transform section, the stress distribution will look a little bit skewed because basically the materials at the way which materials experience stress is some take more load than others. Particularly steel can take a lot more stress than timber, and that's why it gets spread out kind of like that. Okay. All right, I'll move on. Okay. So essentially, that is like a transform section. So in this, I have transform. I have more circle. No, I haven't. Okay. Do you guys find deflections confusing? No? Do you guys want me to go through deflections?
Yes, bro. Yeah.
Go through everything?
Do my exam.
Okay.
Bro, straight out.
Just 1 second. Would you guys want to do this question? Or do you guys want to do this question?
This one.
This question?
You don't have to.
Okay, so deflection questions can be pretty long-winded. If you get a deflection question, I'd say you're most likely to get one deflection question, one inertia question, and then the last question is a toss-up between shear flow and torsion. This might take up most of your time, I'm gonna say right now. Unless you're really confident at this and you're really you know what you're doing, then it will be the fastest question. It's just one of those types. Okay, let's find equilibrium. Essentially for deflection, you're always going to be given an indeterminate beams. So indeterminate just means that you won't be able to find all reactions all at once. You have to solve them through simultaneous equations. So when you solve for, When you solve for Fy and Ma, it'll come in terms of it will come in terms of your reactions. So you won't actually get a numerical value for your reactions. Then we can say that Fy is going to be 5 times 20 minus 10 plus Ay plus By. Times 4, sorry. And then Ay plus By is equal to 30. So that's going to be your equation 1. Then for Ma is equal to 0, you get Ma plus 4By minus 10 times 6. I'll just show the question again just in case, because I feel like I went too fast.
Which paper did you get this question from?
This one's 2018. I'm not gonna lie, some of the deflection questions can get pretty cursed, so. Okay, I'll just move on now. So we're pretty much, right now we're just solving the reactions for this. So you get something that looks like Ma is equal, plus 4By is equal to 60. And that'll be your equation 2. Yeah, that one's just ENGG2400. Don't freak out in the exam if you can't find it because you're not supposed to find it yet. So yeah, just know if it's indeterminate, if it's a deflection question, you won't be able to find the reactions straight off the bat. All right, and now our boundary conditions. So in your slides, in the lecture slides, there is something like this. It's just saying that this is deflection. V is equal to deflection, and dV over dx, I'm pretty sure is rotation of something. I actually not sure. We never use it. But all you have to know is that at those specific points, then those values will be 0. So.
Could you roll up again, please?
Okay, so what it's saying is at yep.
For the moment around A, are you meant to include the load force 5 kilonewtons per meter times 4 meters? So it would be negative 20 times 2 as well.
Yes, you are. Thank you.
Should be 55.
Thank you very much. Yeah. Okay.
Is it By is 55?
Is what?
By.
By is 55. No. You have MA. Is this meant to be 100?
Yeah.
What? 20 times 2? 40? Oh, it is 100. Okay, cool. Okay. This is, okay, we'll go back. This is V equals 0, dV over dx equals 0 at this point and at this point. So that's essentially what your boundary conditions are. To officially write it, you'll just write at x equals 0, V equals 0, dV equals 0. And then at x equals 4, V equals 0. And then that would just be how you answer the question. It's a little bit fast. So now we have our step equation. And you guys are familiar with cutting the beam, right? So essentially your moment equation comes from something that looks like this. And it becomes a little bit more confusing when you do have a UDL at the very beginning of the beam. Okay. So when you should do these questions, you should always put your cut after the support. So at the very last support, let's say you have like a beam that's like as long as this. Right? You should always cut it here. So in this case, we're going to be cutting it after this support, and then the rest of this part is cantilever. So I mean, you can still write it, it's fine. But this is 4 meters. This part is 6. So we're taking the moment around x. We're taking the moment around the cut for the distance x. So x is just any random number after 4, in between 0 and 2, because that's the distance of the cantilever. So yeah, and when you're doing your step function, it should be it should just include everything that you have. So one thing to particularly note with UDLs, especially if they're like before the cut and they end before the cut, is you have to extend it. So this is just like something that makes it a lot easier for you. You have to extend it, but if you extend it, you have to add 0. So you have to add an equal and opposite on the other side. This will just cancel out that moment if you cut it there. So that's just what you have to do. And it's a lot easier than just trying to minus something from another and trying to do that. So I would say this is the most recommended route. It's the fastest route that I found. And you'll find that this distance here is x minus 4. Okay, so let's go from the very left to the very right, and we'll start off with mx actually. So mx, that's just your equation. So mx plus ma minus ayx. Yep. And then you have plus, we'll do the reactions as well, minus by x minus 4. Okay. And then we have the UDLs. So that first one, the blue one, is going to be 5x, 5 times x on 2. And then the red one is going to be minus 5 x minus 4 x minus 4 on 2. Yep. And you should get a moment equation. So mx is our moment equation. That looks like this. Okay, do you guys, what are you guys confused about?
Aren't we already determined AY and EY?
Huh?
Can't we already determine AY and EY?
No.
How can we have that
This.
all the way back in the reaction?
Yeah.
How do you find it out?
If you take the moment around A, MA.
You take the moment around A.
A plus B.
If you take the moment, this is the moment around A.
MA plus MB.
Yeah.
Yeah. If you sub this into this, you get an equation that's in terms of MA and AY.
Yeah. I'm just confused why you include the term
Because wait, here.
in MA plus 4BY.
Because if you're taking the moment around the area, you still have the reaction.
Because
Like-
when we do the assignment, we not included the MA inside, and the answer is right.
So this is like the moment around A, which is going to be this.
And then we can identify AY and BY if we not include the MA one. In our assignment, we do like that.
That's weird. Basically, what this is saying is this is MA. So this is the internal moment MA, and this MA here is the external moment MA. So that's the moment that's in purple is a reaction force. The one that's in red is the internal force. So when you have, you know how like when you have a bending moment diagram, like it should start at 0. The bending moment at MA can't start like somewhere here, essentially. So there needs to be a reaction force that puts it back down to 0. That makes sense. And a cantilever is a fixed support, so it will have a bending moment. It will have like a moment reaction. Yes. Okay. Does everybody understand how I got the step function?
Yep.
Okay. And you guys know what the diagonal brackets mean?
Okay. Wait, sorry. Can you no to both of those questions.
Okay. So I'll start with how I got. I'm guessing the confusing part is this side, right?
Somewhat, yeah.
So okay, I'll explain this. So mx comes from the cut. So there's always going to be an internal moment.
I do get that part.
Yep. Then there's going to be ma, which is at the very end. Then there's going to be the distance ayx.
Yes.
Then it's going to be the distance by x minus 4. Okay, and now for the cantilever, it's the magnitude of the UDL, which is 5x.
Wait, but don't we know?
No, we're extending the UDL.
Oh, what? Why?
Because it's too cursed if you don't do it. Basically, if you don't extend the UDL, then you find something that is like it's going to be like, that is going to be x minus 4 on 2, and then you have to find like the distance of that on half, and then it's like just way too cursed, pretty much. Yeah. And it doesn't even work out like half the time. So you're just extending the UDL, you're adding 0, which is the red part. So this,
Yeah, 0.
yeah, so the purple part is what we added. We're adding 0. So to add 0, you add the same in the opposite direction.
Okay.
So this red part is just the purple part, but zeroed. Yeah. So it's going to be 5x, which is the whole distance this time, times half of that distance. And then the very last part, which is this part, is counting for half of this part. So it's the magnitude of 5 times x minus 4. That's the distance. That's the magnitude of the UDL. And then the lever arm is x minus 4 on 2.
Where does the x on 2 and the x minus 4 to?
These ones?
Yeah.
They're from the lever arm. This is a moment.
Alright.
Yeah. Like this is the lever arm here, and that's the lever arm there. Yeah. Alright guys, we're going to move on. Sorry about that. Okay, so from your notes, you should know that your deflection looks kind of something like this. Yeah, and that means that your Bx is equal to 1 over EI double integrated mx dx dx. Right? So essentially what this means is you have to integrate twice. And there's no other way to do it. So you have to integrate. It's not as bad as like if you didn't do integration or you weren't really like wasn't really a strong point, it's not really that bad. I'm not gonna go through like how to do it, but I'll just go through the motions. So okay, the first integration is mx dx, and I'll just copy and paste this so you guys can see. But essentially, you get ayx squared on 2 minus max plus by on 2 x minus 4 squared minus 5 on 6 x cubed plus 5 on 6 x minus 4 cubed plus c1. And then you get this, and then you just integrate again. And you should get something that looks kind of like that. Let's move this to the side so it's easy to see. Okay. And you'll notice that we have these two constants. And these are solved by the boundary conditions that we solved earlier. So that was at Vx equals 0 and dv dx x equals 0 equals 0 equals 0. And you'll find that C1 is equal to 0 and C2 is equal to 0. So then Vx EI is equal to ay on 6x cubed minus ma on 2x squared plus by on 6x minus 4 minus 5 on 24 x4 plus 5 on 24 x minus 4. And then that's your equation for deflection. And now you'll actually notice that we have an equation now in terms of ay, ma, and dy. So now we can actually solve it. We have ay plus by is equal to 30, ma plus 4by is equal to 60. And just, you can solve this any way you really want to. I think the easiest way is to put it all into one term. and then you you substitute into the last boundary condition. So the last boundary condition was Vx equals 4. That's at the roll support. That also equals 0. So then you get something that looks kind of like this. This is meant to be 100, sorry.
The hard part's getting the end. They have carry on. But like, I mean, like, just make it nothing around you and maybe especially if there's more.
Yeah.
You understand? Why if you lose 5K, you cry. You even have 5K to lose. Where'd you even get that money from? I've been hitting it every weekend. What page? You actually can't lose anymore.
Unless you're Nick.
Yeah, if you size correctly.
Yeah, 30 on 6 times 4 on 2 minus y on 6 times 4 on 3. Okay, the last part of this question is just crunching through the numbers and trying to find your simultaneous equation. Should get something that looks like this. By is equal to 3 on 6 minus 3 on 2. And then when you divide this side by this side, you should get your by. And when you get your by, you can find your ay. And when you get your ay, you can find your ma. So since I've followed through with the reaction is 60, I've actually got this wrong. This 100 changes. I don't know what the reactions are though right now. But essentially, what you would do is you would sub ay is equal to whatever, ma is equal to whatever, by is equal to whatever. And then you would actually sub in whatever you're interested in. So you just have to look back at the question again. I know I haven't really been looking at the question, but your last question is to determine the deflection at point C in terms of EI. You'll notice that C is at x is equal to 6, so you would plug in Vx equal to 6, and then you would have to find the deflection at the very end. Yep. So before we continue on to the next question, I'm just going to confirm the my thing. So we would have got this equation. So this is from your week five lectures, and essentially the y is the distance of your point of interest to the neutral axis. So in this example, in this example, they're taking this point here, and then they're just measuring y. So I think trying to think of the best way to say it. So essentially, I think that this is positive y, and this is negative y, and the reason why we got the signs flipped is because actually, I know why. It's because I think this part. Where is it? I think this part is meant to be negative. I think this part is meant to be negative. Wait, is it?
Area is positive though.
Is it negative? It's positive.
It
is negative. So basically, so I kind of screwed this up. The maximum moment, the internal moment here, internal moment at the very end point, which is point B. Let's just say this is B. Is actually 10 kilonewtons per meter, right? Oh, is it? Yeah. So this will be bending down. This will be bending like this, right? And then when you do sum of moments around A, you get 10. Oh, what the hell? Wait, is it? 10 minus MA? Wait, I'm kind of tripping. Okay, essentially, what I think is happening is this reaction is MA. There's some MB here. This distance 10? 1? Yeah. I guess you could just actually just do that. It's minus 10 plus. Oh, what the hell? Okay. I'm actually not 100% sure. I think it should be negative though. Weird. Okay, basically, I think that's where the error is. I'm not sure where the error is, but I think it's here, and your MA should be negative. Okay. Let's move on to. Do you guys want to go through shear flow or torsion? Hands up for shear flow. Okay. Just a disclaimer, I didn't get tested on shear flow, so I didn't actually study shear flow. The most shear flow content that I have for you is what I cooked up at 2 a.m. last night. Okay, so from my understanding of shear flow, my very brief understanding, we're going to look at this question. And what shear flow is mostly just finding out, like, when you have a beam that bends, you have a bending moment and you also have a shearing moment, or like a shearing stress. So you have normal stress, axial stress, and you have shear stress as well that comes along the beam.
Internal will be like the opposite side.
Are you sending us this?
I'm gonna fix everything and then I'm gonna send it again.
That's cute.
Yeah, I'll probably send it to the fluids tutor after, or it'll be up like on the website or something. Yeah. Okay, so.
down one.
Okay. So, according to disclaimer, don't take this as Bible. It could be very incorrect, but it's just kind of a general like way you should go with the question. Okay. So if like this is the case that you have no idea what you're doing, you feel like you need some steps. I think I know the general steps to get there. And it's just the way you execute it. The way I execute it might be wrong today, but I'll just try and help you. So, yeah. So basically with shear, it's kind of the same thing as deflection. No, not deflection. With the inertia stresses, you're trying to find the most extreme moment at the most extreme point at which your moment or shear is going to happen. So if you remember for the first part, the transform section, we were looking for the part where our moment was shear, our moment was maximum. We're looking for the part where our shear is going to be maximum in this case. So you kind of know generally that for your beam, your shear diagram is going to look like this. And you can kind of very easily tell that your maximum shear is going to be at your very ends, right? In the case that you get something that looks like this, like that, then you would have to calculate shear here. Okay, but in this case, we can kind of take this really easily. 5 times 10 times half is 25. And you can just kind of say that both of those reactions are 25 kilonewtons. And that means your Vmax is 25 kilonewtons. Yeah, that's the entire question. Okay. And since this is symmetrical, you can say like this is symmetrical along the x-axis. You can say that y bar is going to be 20 plus 50, which is 70. This is just like if you have symmetrical perfect values, by the way. So if you don't have anything you have something that's irregular and composite, then you have to find them the conventional way, which is by doing the summation. But let's do IXX and IXX2. So IXX1 is basically the flange. For shear flow, you might have to know like these conventions. So this is called a flange, and this thinner part is called a web. So yeah, we're gonna take the inertia of the flange because the two flanges are identical. And the dimensions for those are going to be 50 times 20 cubed over 12. And that one's going to be 20 over 100 cubed times 12. You end up with 3.3 and 1.666. So these are just stepping stones. These are just stepping stones because you need them in this equation. So that's going to be your shear. This equation that I'm pointing at right now, this denotes your shear at a specific point. Your Q essentially is like what they call it is, this is what you actually use. So if you remember in your inertia notes, like you have y, and then you have q, you have qx, and you have ix. Like ix is your second moment of inertia. Oh, sorry, second moment of area. Qx is your first moment of area. And that's the only part of it. This is the only time in the course that I've actually seen qx been used. But the formula for that is BD cubed on 12, as you know. This one is just area times y bar, I'm pretty sure. So that's what that is.
Is that total area?
Yes. It's basically it's the area of like all of the components. So Okay, this is where it gets a little bit dicey. This area is 50 times 20. And I'm pretty sure you're taking it from the neutral axis. So the distance of one flange, is going to be 60. And then this is the web part. So the web part is 20 times 50, that's the area, times 25 on 2. I'll see if I can redraw this. Maybe I can. So okay, you might be asking like, is there another shape? There is another shape. I think it doesn't really matter because when you're drawing a shear stress distribution for I-beam, it should look something like this. And essentially, it's symmetrical on both sides. You only need to take it like we're kind of imagining that half of the beam is cut, and then we're just like taking on the top side. So this part will be 72.5 MPa, I think. I believe. Oh no, sorry, that's wrong. That's just the Q. Now your shear, which is noted by tau. Tau is VQ over IB, and it's just plugging in values. So you get 25 times 10.3, which is your shear, your max shear, times 72,500, and then your IX and your B, which is equal to 20, and you should get something that looks like 52.2836. And basically what that means is like this is the neutral axis. This will be 52.286. And then what we're doing is we're solving these extra points. So you know that this point will equal this point, and like these 2 points will equal these 2 points. It's kind of similar to the shear stress thing where like you have to find the stresses for the actual stresses, but like the shear stresses you have to find for before and after, because a little bit before is the flange and a little bit after is the web, pretty much. And that is done a little bit. That is done in like a formulatic fashion. So essentially, you're only considering the shear in the web. If you're considering the shear in the web, then you're only taking this part to be like completely static, and you're moving your y throughout the web. So if this is your neutral axis and you're moving your y, then this will be like the distance between like half the web, and that will become your new y. So when you're actually calculating the first moment of area, you need to come up with something that is in terms of y, because your shear flow then, your shear stress will change with how y is changing. So you get something that looks like this. You have your flange, which is 50 times 20 times 60. And then you have something that looks like 20 times 50 minus y plus 50 minus y on 2. That's the area of the width of the web, and then that's the distance to the web center. And you get something that looks like this for Q. And this is where my solution stops, so I need to rely on something else. But essentially, now you're plugging it back into this equation. And basically at the web, it will denote the shear stress on all of this part. So essentially when you're moving down y, this shear stress will change. And you're moving up y, this shear stress will change. And that's just what this formula is saying. So you get you get tau is equal to VQ over IB. And it will look something like 25 times 10 over times 85, 100 minus 10y over IX times the breadth of the web, which is 20. So yeah, after you put that into some sort of equation, you'll have something in terms of y, and then you can move on to the next part. So move on to the next part. This is at flange. So going step by step, we solved for the shear stress at the neutral axis. We solved for the part where like it's in the web, the shear stress in the web, and now we're going to solve for this last part in the flange. So now you have something that looks like this. And let's say that this is the neutral axis. And essentially, this is like if the flange was cut, by the way. Like that distance isn't 20. Yeah, it's not 20. So this distance will be this distance is 70. 70 minus y. This is y. And this distance will be y plus 70 minus y over 2. And then that will be what you plug into Q, and then what you plug into tau for your shear. And just by doing the same thing, you get the area, which is 50 times 70 minus y. Minus y times the distance 70. Oh wow, y plus 70 minus y on 2. Oh, and that's it. You should get something in terms of y. I don't actually know what that is. 35. Oh. Okay. Anyways, you guys kind of get the point. You're just putting this into a thing where you have something like a equals by plus by squared. And then your shear. Your shear will be the same thing, 20 like V and then plus this. All over IX. And your B in this case will be 50 because the width of the flange is 50. So B here is 20 because the width of the neutral axis is 20. B here is 20 because the width of the web is 20. And B here is 50 because the width of the flange is 50. Yeah. Then you'll get another equation in terms of whatever that is. I actually don't have the numbers for you, I'm really sorry. And basically, what that means is you can find what these numbers are now. So you know that yeah. You know that this is y is equal to 70. This is y is equal to 50. This is also y is equal to 50. And then this is going to be y is equal to 0. And then this will be negative 50. That will be negative 70. And basically, you take this to be your at web, this to be at flange. And you plug in your value. So this will be something in terms of tau y, and and you also have tau y web. You would plug in these specific numbers. So you would plug in tau flange 70, tau flange 50, and then you would plug in tau web 50, tau web tau. Wait, what? Oh, yeah. You put in tau web 25 because I think you're interested in this point as well. Okay. And that will be your shear stress distribution. So then you could say, the question is as well asking for spacing required for screws and what is the maximum shear flow in section and where does it act? Someone else can probably answer this better and confirm this, but I think shear flow flows like this. Right? And as you found out, your maximum shear will be at the neutral axis. If you have something that's a little bit more skewed, like a T.
Where do you get the A and the B from that equation before?
This one?
Yeah.
It's from this. I just don't have the calculator to pump it in.
Yeah, but what's A and what's
It's A is the constant, B is the coefficient of y squared.
Oh.
Yeah. Okay. And then, like, for example, if you have you have to watch out if you don't have a symmetrical shape. If you don't have a symmetrical shape, it can change because the shear of your shape could look something like this. That's for a T shape. And then your T max. Your shear max will be instead at the flange, where the flange and the web meet. You have to be careful where you take your shear max, and that's how you do it. I don't think I have time for torsion, but and I also don't have time to do the spacing. But the torsion is quite straightforward, I'll say. if you look at this question, essentially it's getting information from the question, listing it all, and then just plugging it into numbers. So what it's saying is essentially, most of the questions will be in the format of what is the largest torque you have to apply to this certain like cylinder to make it like not exceed a certain amount of degrees. In this example, it's 2. So basically, you can't spin it. Like how much force can you apply to it before it exceeds 2 degrees in spin? This is just using material properties. Material properties are given to you every time, and it is just kind of like a cookbook thing. You just have to follow the formulas. Yeah, and then it will give you like certain values. One thing to note, this is kind of similar to most of your other courses you might be doing in 3rd year or like end of middle 2nd year or end of 2nd year. There's something where you'll get a lot of values for one particular number. So for example, you'll notice that we have, this is capital T. This is called torque. Essentially it's saying that when torque is 715,000 newtons millimeter, the aluminium rod will fail. Like fail in terms of like just it won't be able to spin anymore. And for steel failure, that only needs to be 173,000. Now for the maximum torque, which is allowable, that is 2 degrees. You also have to calculate that. So for torque questions, you should be getting 3 torque values. And you always take the minimum one, because the minimum one is the most extreme one. So like, it doesn't matter if you apply 10 kilonewton meters of force if something will fail after 1 kilonewton of force, if you get what I mean. So you always take the minimum one, and that will always be the minimum allowable one. You'll find that you'll have a lot of capacity has to be larger than loading. That's just essentially what this is. The capacity in this case being like how much can what the failure of the rod is, or what the allowable is, and then the loading is how much you're actually putting on. So, yeah. Okay. And that is pretty much the whole question. Torsion is quite fast, as long as you kind of know like what the formulas mean. If you feel like scared that torsion is going to be in your exam, just study what the formulas mean. Just do like 2 questions. I think it will click really fast. So, yeah. Yeah. Otherwise, if you guys have any other questions for me. Okay.
Do you remember your old exam?
I do remember my old exam. I can get it up.
What do you get?
Yes, if you spend too much time on inertia. There's 2 ways to do inertia. Like inertia can eat up a lot of your time if you just like kind of don't really know what you like how to do it. Inertia is the one you need the most practice for, just because like it's so much writing. Yeah. Okay, this is last year's exam.
Wait, do you have the answer for that paper?
For this paper?
Because I just did that paper, but I want some solutions.
I have solutions for the first question.
Oh.
But the other two I think is okay. Like this is like the sorry. This is like the first question we did. This is like the second question we did. Oh. It's like the question we did. So we didn't actually do, like for my year, we didn't actually do shear flow, we didn't do torsion, and we only did deflection, inertia, and inertia. Like the only thing that was a curveball was this question, I would say, because plastic moment is like mentioned like once or twice in the course, and they threw it at us. Yeah. Plastic moment is essentially, I can explain it. Okay. So the difference between plastic moment and normal yield moment. So you have my and you have mp. Basically, this is a stress strain diagram. Are you guys, who did Maths 101 last year? So you guys will already be familiar with a stress strain diagram. You'll know that this is a elastic region, and this is a plastic region, right? Basically, what it's saying is, you know how a stress distribution looks like this? As something becomes more plastic, it doesn't get stronger. Like this, if this is 275 MPa, if you keep straining it more and more, then it's not going to exceed 275 MPa. Instead, the rest of the section is going to start deforming like this, where this is 275, this is 275. And when you have a fully plastic moment, it will look like that. And if you need to find a moment, there is like a formula. The best way to do it is to take the area here, take this, and sum it around. For this question in particular, the moment looks, the stress distribution looks something like this. Things like this. Oh, sorry. Things look something like this, where you have a stress and then it gets larger like that. So then you have to do this. You have to find shape 1, shape 2, shape 3, shape 4. And then you have to take the moment around the neutral axis, find this lever arm, find this lever arm, find this lever arm, find this lever arm, and then sum it all together. So that's how you would do a plastic moment question, like this one in particular. It is definitely different to like other questions, but it is something you can get, and it is something that can be tested. If you're wondering about how to get moment in any case, like as well, it's the same thing here. You can find the moment by taking like summing up the side of the stresses as forces, timesing it by area, because that's that is just stress is equal to F over A. So F is equal to stress area. You just have to transform it into a normal force, and then you would have to find the lever arm. Yeah. That's that question. The bottom ones are ones that we did. These ones you guys should be able to do, I think. Yeah, this one was a little bit cursed because this one is both fixed ends. So both of the sides had fixed ends. You had to find, when I did this exam, I don't know if my approach was even correct, but basically I had two moment equations because I had to take one with in terms of MA and MB. So I had to have one equation in terms of MA, and I had to had one other equation in terms of MB, because you have 4 unknowns. So you need 4 equations. Yeah. Yeah, just know how many unknowns you have. That's how many equations you need, and then try and find it kind of find it accordingly. So I cut it from the right, and then I also cut it from the left, and then I had to find 2 deflection equations. Yeah. If you want this exam or a bunch of other exams, I'll put it onto the folder that I'm going to be uploading the notes on. Yeah. But otherwise, that's it. And thank you very much. I think we might set up a drive. If there's no drive, then I will just. What should I do?
You want to make a drive now, so we've been like all locked into it.
I'll actually upload it to my drive, and then it will come underneath the YouTube video description. Yeah.
What YouTube video description?
Can you put the link to
The YouTube video will be up on CEVSOC YouTube channel, and then you'll be able to find this recording and a lot of other previous recordings. So. Sure.